From this, I can find the Lagrangian. L is t minus b, which is 1 over 2 m L squared theta dot squared minus 1 by 18 k L squared theta squared. Now I can use the full complete Lagrange equation of motion, which says that d by dt partial Lagrangian partial q dot. In this case, our q is theta, so this will be relative to theta dot plus partial anticipation function partial theta dot minus partial of the Lagrangian respect to theta equals partial the work with respect to theta. Now I will substitute all these functions and the Lagrange's equation of motion. Let's derive those terms one by one. The derivative of L with respect to theta dot, we only have this term, so it's m partial L partial theta dot is 2, those we have, so it's ml squared theta dot, and if I take the complete time derivative d by dt, this becomes theta double dot. Now, the partial derivative of the dissipation function with respect to theta dot is, this is straightforward, 2 times 2 is 4 divided by 9 c theta dot, and the derivative of the Lagrangian with respect to theta partial L partial theta is, here's the Lagrangian, this is constant with respect to theta, so I'll end up with just 1 over 9 negative 1 over 9 k L squared theta. The partial derivative of the work with respect to theta is simply f of t times L. Now I have all the expressions I need to complete my equation of motion, which becomes m L squared theta double dot plus 4 divided by 9 c theta dot minus is plus 1 over 9 k L squared theta equals f of t times L. Now I can plug those numbers into the equation of motion. The length is 1.5 meters, so and the mass is 32. So 1.5 squares 2.25 times 32 is 72 theta double dot plus, I guess we're missing a term here. It should be L squared here. L squared C L squared. So L theta equals f of t is 50 times L is 1.5, that makes it 75 cosine 2 pi t. And now this is my equation of motion. Although the original terms are not mck, but this equation of motion looks much like the mck, but they're equivalent, m equivalent c equivalent k, but the same applies as long as you have a differential equation, second order, represents the equation of motion. The coefficient of the second derivative is the inertia term, and we can always refer to it as m. The term with the coefficient of the first derivative is the damping term, and the coefficient with the variable itself is the stiffness term, and this is the forcing term. So now I can normalize this equation with respect to the mass, get the mass normalized equation of motion, which is theta double dot 2 zeta omega n theta dot omega n squared f0 cosine omega t. Let's proceed and try to find the steady state response. Here, this is 2 zeta omega n, and this is omega n squared. So I can find omega n, which is the square root of 8.333, and that comes out to be 2.887. 2.887, and that's of course radians per second. And then I can substitute this value right here and solve for zeta, which is 0.4167 divided by 2 omega n, and that comes out to be 0.0722. And it's a ratio, so it has no units, and we notice that the system is lightly damped. It's very low damping ratio. The forcing frequency is 2 pi. I already have that here. So now I can find the particular solution or the steady state response, which is x times cosine omega t minus theta, or I can find it in the other form, which is a cosine omega t plus b sine omega t. Either way, we have the expressions for x and theta, or a